method within second order accuracy, and the speaker will be Professor, Suzuki. That yes. I think, yes. So it's your time to take the stage. I can hear you.
Okay.
So you have to take the presentation, start the presentation. So I remember you have 20 minutes to be.
Can you see?
Yes, perfectly.
Okay.
The stage is yours.
Okay. Thank you, Chairman. And this study focuses on the fundamental of the forcing schemes in the lattice-Boltzmann method. Okay. So it is well known that when the Knudsen number is of order of the non-dimensional lattice spacing delta x, the Reynolds number is finite, the Mach number is the same order as Knudsen number, and all variables varies smoothly and moderately. The solution of the lattice-Boltzmann equation satisfies the incompressible Navier-Stokes equation system with relative errors of order of delta x squared. In addition, we need to combine the forcing scheme with the lattice-Boltzmann equation in order to consider the external body force. So far, many forcing schemes have been proposed. Okay. Among many forcing schemes, the simplest one was proposed by He et al., and we call it He forcing. In this presentation, we consider the single relaxation time LBM with the non-dimensional variables normalized by the characteristic variables as shown here. Especially, we use the diffusive timescale. In this scheme, the forcing term is added to the time evolution equation of the velocity distribution function, and this forcing term is given by this simple form. Although this is the simplest forcing scheme, the Chapman-Escock analysis by Gore et al. Have shown that the unphysical terms appear in the macroscopic equations due to the spatial and the time derivatives of G. On the other hand, Gore et al. Have proposed a forcing scheme as well. This is most popular among many forcing schemes, and we call it the Gore Forcing. In this scheme, the forcing term is more complicated than the He forcing. And the body force term is added to the definition of the velocity. From the Chapman-Escock analysis, Gore et al. Have shown that no unphysical terms appear in the macroscopic equations. Therefore, the Gore forcing should be more accurate than the He forcing. However, some numerical demonstrations have suggested a question. Is really Gore forcing more accurate than He forcing? For example, Mohammed and Kazmin simulated the natural convection problem in a closed cavity like this. In this problem, the buoyancy force is added as an external force due to the thermal expansion of the fluid. And this force is space and time dependent. Mohammed and Kazmin calculated the time variation of the temperature at the center of the domain. In this figure, this curve is for the He forcing, and this curve is for the Gore forcing. In addition, we can see that the analytical solution should be 0.5 because of the symmetry of the domain. So from this result, we can see that the He forcing gives almost the same or slightly better than better result as Gore forcing. So this contradicts the conclusion of the Chapman-Escock analysis. This contradiction might be attributed to the assumption in the Chapman-Escock analysis about the leading order of the body force. The Chapman-Escock analysis usually assumes that in order to be consistent with the remaining terms in the LVM, the forcing term must scale as Fi equal order of epsilon, that is the order of Knudsen number. In other words, the leading order of the body force is assumed to be of order of delta x. On the other hand, from the physical viewpoint, it is natural to assume that the body force is comparable to the time derivative of the velocity in the dimensional form. This leads that the characteristic body force is comparable to the characteristic flow speed squared over the characteristic length. This assumption corresponds to the finite fluid number when G0 is gravitational acceleration, for example. So this assumption is natural from the physical viewpoint. In the non-dimensional form, the body force should be comparable to the square of the ratio of the flow velocity to the particle velocity. Because this value in the parenthesis is comparable to the Mach number, so the leading order of the body force should be delta x squared. So the assumption of the in the Chapman-Escock analysis is not consistent with the physical consideration of the leading order of G. Due to this inconsistency, the Chapman-Escock analysis might lead an overestimation of the errors of the shear forcing. Okay, in the present study, we analyze shear forcing and Gore forcing by using the asymptotic analysis instead of the Chapman-Escock analysis in order to analyze more precisely. In the asymptotic analysis, we expand not only the velocity distribution function, but also the macroscopic variables by a small value, delta x. Note that in the macroscopic variables, the density, the first term of the density is constant, and the perturbation of the velocity starts from of order of delta x. This is because the deviation from the equilibrium state at rest is Mach number, so is comparable to the Mach number, so comparable to delta x. In addition, the perturbation of the body force starts from the order of delta x squared, as shown in the previous physical consideration. The equilibrium distribution function, FIQ, and the forcing term, capital Fi, are given function by the macroscopic variables. So these given functions can be expanded as shown in these equations, and the coefficients in the expansions are given by the macroscopic variables as shown here as well. The expansion of the equilibrium distribution function is the same between the shear forcing and the Gore forcing. But the expansion of the forcing term is different between the shear forcing and the Gore forcing because the definition of the forcing term is different. Okay, let's start the asymptotic analysis. Step 1, we perform a Taylor expansion of the Boltzmann equation around x, t, and we can obtain this expanded form of the Boltzmann equation. Note that in the diffusive timescale, delta t is equal to the Strouhal number times delta x, where the Strouhal number sh is of order of delta x. So in this equation, these coefficients are of delta x. Then step 2, we substitute the expanded forms of Fi, Eq, and capital Fi into this equation. Then step 3, we can derive the partial differential equations of Fi for each order, 0, 1, 2, 3, and 4 by equating the terms of the same order of power of delta x from the previous equation. And finally, we can derive the macroscopic equations for each order k from the solvability condition as shown here. It should be noted that the solvability condition is different between He forcing and the Gore forcing, because in the Gore forcing, the definition of the velocity includes the body force term like this. So from these conditions and previous equations, we can obtain the macroscopic equations for k equals 0, 1, 2, 3, 4, and so on. Okay, let's see the resultant macroscopic equations for He forcing. These are for k equals 2, k equals 3, and k equals 4. Among these equations, we can find these two equations are the incompressible Navier-Stokes equation system for U1, rho 2, that is P2, and G2. In addition, we can find that these two equations are homogeneous linear equations for U2 and P3 when G3 is 0. In many problems, the body force should be determined only by the leading order term G2, so we can set G3 to 0. In general, the solution of homogeneous linear equations with 0 initial and boundary condition is 0. So U2 and P3 are 0, should be 0. As a result, from these two sets of equations, we can see that U and P obtained by the Boltzmann method satisfies incompressible Navier-Stokes equation system with relative errors of order of delta x squared. The remaining equation here contains higher order terms outside the second order accuracy. Actually, this equation includes the unphysical term in the right-hand side due to the derivative of the body force. But this unphysical term is outside the second order accuracy. So this term does not affect the accuracy of the LBM. On the other hand, the macroscopic equations for Gore forcing are the same as the He forcing, except this equation. In this equation,
Mr. Okay. Suzuki, you have 5 minutes left.
Okay, thank you.
You're welcome.
In this equation, no unphysical term appears. This is some kind of improvement of the Gore forcing. However, this term is outside the second order accuracy. So in conclusion, He forcing and the Gore forcing should be equivalent within the second order accuracy. In order to verify this conclusion, we simulate a generalized Taylor-Green problem. In this problem, the box is with size H0, convect, diminish, decay, and amplify periodically due to this time-dependent body force field. This external force varies periodically in space and time. The boundaries of this domain are all periodic. In this problem, the analytical solution of the incompressible Navier-Stokes equation system can be found, as shown here. This shows the errors from the analytical solution for pressure P, velocity U, and the divergence of the velocity. When the derivatives of the G of the body force are not 0. The circles are for the He forcing, and the squares are for Gore forcing. So from this figure, we can see that both forcing schemes have the second order accuracy. In addition, the magnitude of the errors is almost the same. So the two forcing schemes are equivalent in terms of the accuracy. Finally, we simulate a new natural convection problem in a closed cavity. In this problem, this buoyancy force is added as an external body force due to the thermal expansion of the fluid. The flow is initially at rest and tends to the steady state like this. So this force varies in space and time. Unfortunately, the analytical solution of the problem is not known, but we can check the equivalency of the two forcing schemes by calculating the difference of the results. This shows the difference between the two forcing schemes for pressure, velocity, and temperature when the state is still unsteady. From this figure, we can see that the differences between the two forcing schemes have the second-order convergence rate. So this means that the He forcing and the Gore forcing are equivalent within the second-order accuracy. So the conclusion of the asymptotic analysis has been verified. In summary, the leading order of the body force can be derived as of order of delta x squared from the physical consideration. And the asymptotic analysis for the He forcing and the Gore forcing shows the two forcing schemes are equivalent within the second-order accuracy. This conclusion has been verified through two benchmark problems where the body force varies in space and time. This study has recently been accepted and will be published in Physical Review E. So for more detail of the analysis, please refer this paper. So thank you very much.
Okay, thank you very much to the speaker. Then we have time for a question. There is a pre-notation by Sayed, so you can present your question, please.
Yeah, can I ask a question here?
Yes, yes.
Yes. It's interesting work now. It's more of a comment than a question. So I think the Gore forcing was developed particularly in context of multi-phase flow. And for multi-phase flow, of course, we get surface tension terms which formally don't come out of a second-order analysis. Basically, the surface tension terms in the Navier-Stokes equation are formally already of a higher order, so that you actually do need higher orders in these gradients to be able to describe that correctly. And if you look in the system, and we did an analysis, which I think you cited in your paper as well, for thermodynamic consistency of these various methods, which comes up with a slightly different version of something that looks like the Gore forcing. But there's actually measurable differences and measurable improvements, certainly looking at these multi-phase flow problems.
Yeah, as you said, in the multi-phase flow, the He forcing and the Gore forcing has some measurable difference. But this does not mean that which is better, He forcing or the Gore forcing in the multi-phase flow, because in the multi-phase flow, the body force has a very small support, and the derivatives of G is very large. So for this case, we have to perform asymptotic analysis with other, how can I say, other assumption. So we have to change the asymptotic expansion in such a case, I think. Is this answer for you?
Yes, thank you.
Okay, I think we thank again the speaker.
Thank you.
Then we can move to the next one, is again Giacomo. And the title of the presentation is HPC simulation of Euplectella aspergillum underwater hydrodynamics. So now the stage is yours, Giacomo.
Thank you very much, Giorgio. I am sharing my screen. I hope you will see it. And,
yes, we see something, so I think...
Good afternoon to everybody. Thanks, Giorgio. So I will show you the results we have obtained in our research groups, both at university from Tor Vergata, at the IIT with Succi, at Cineca with George Amati, the chairman, and the activities started at Harvard University, talking to the group of Professor Katia Bertoldi and James Weaver. So don't worry, I will tell you what is Euplectella aspergillum. We will see what is the problem description, we will see the implementation, and then we will discuss the results. This is Euplectella aspergillum. It is also known as Venus flower basket, as it is written here, is a glass sponge of the phylum Porifera, and it is a marine sponge, a rigid structure, which dwells in the bottom of the oceans, the Pacific Ocean, especially in the most southern part towards the Antarctica. It was catalogued in the late 19th century. It was also emotional. The reports. The first one was the report of the voyage of HMS Challenger during these years, 1873, 1876, under Captain Generalized. Also work by Owen, the catalogation, the first catalogation of this Euplectella aspergillum. This sponge has a truly remarkable structure. It is made by silica, so it should be as brittle as pure glass, but instead it has a minimum of structural properties, and these structural properties rise from this very complex hierarchical ensemble that the animal builds in order to construct this skeleton with these remarkable properties. So the hierarchy is really complex. This is the most cited paper on these structural properties by the group of Eisenberg and James Weaver at Harvard University, Science 2005, and the hierarchy, you see, goes from the size of these sponges are usually tall 20 centimeters maximum, otherwise below, so from the order of 10 to 1 centimeters to you can see it down to 1 nanometer. Okay, so the structural properties are granted by this multi-layering growth of this silica structure interposed by organic materials, and this grants the minimum structural properties that allow the animal not to die immediately. So the remarkable structural properties have been viewed upon in the last 15 years by many authors, but no one has ever attempted to thoroughly investigate the full-scale fluid dynamics of this sponge. Just 2 papers are present in the literature. This one by the group of Professor Wetzel, but they just looked into a portion of the skeleton just to see the flow through the pores. And another one from my group 2 years ago, we were starting this activity and just use equivalent and more simplified geometries. Then we turned to the actual real exoskeleton. So, first of all, before discussing the realization of the simulations, we have to look at environmental conditions. It is a deep sea sponge, so it dwells in marine water between 2 and 6 degrees Celsius. The properties of salt water at this temperature are reported here, and we, most of all, will deal with viscosity, and the sponge is anchored to the seabed, so it experiences usually, normally, velocities in the range of 0 to 10 centimeters per second, 10 to minus 1 meter per second. Given that its diameter is in the order of 4 centimeters, so 4 per times 10 to minus 2 meters, we deal with the Reynolds number, which is in the order of 2,000. This is the standard environmental conditions of this organism. Due to the many works done in regarding the structural properties of this skeleton, exoskeleton, which are, as I told you before, remarkable, we capitalized on the work by the group of James Weaver on Journal of Structural Biology and reconstructed the modular structure, in which are also present some ridges to reinforce the this network, and we arrived to constructing this geometry that has a resolution of is 20 microns. Okay, this is the actual minimum hole that we are able to resolve with this geometry, and it is completely adherent to the reality. We have also introduced some defects which are present in the structure. So these are the external ridges which are known to provide structural sustain to the sponge, to the exoskeleton. There are some holes. There is this double helix interrupts, and there are some holes in the ridges, and then there is a network inside here composed of even lower holes, and these fibers, these glass fibers, intersect with an angle of 45 degrees. Okay, actually the hero for the reconstruction of this geometry was Pierluigi Fanelli, who is really a wizard with the CAD, and we have been working on this a lot in order to reproduce the actual geometry of the sponge. So this is the object. Now, the domain size. According to the regime, in the order of 2000 Reynolds number, we have to deal with the boundaries, of course, and we know that at those regimes the boundaries can create great problems for the reliability of the simulations. We have done many tests with, of course, simpler geometries, basically the cylinder one, in order to create a domain in which we were pretty sure of the non-interaction of the boundaries with the results. And we arrived to this domain in which the silica sponge was posed at, given D its diameter, 9 diameter from the inlet, 18 diameter from the outlet here, and 8.5 diameters from left and right walls. Considering the other view, the domain height is more than twice the height of the entire structure. The problem is that with these numbers, given the space resolution that we need in order to resolve the flow through the single pores, we need a grid of 44.9 times 10 to 9 lattice sites in order to make a simulation of Reynolds 2000 of this object. So this is the reason why this computation, such a computational power, has been the bottleneck to study this structure, the behavior of this structure. So we run the simulations on the HPC facilities, Italian facilities at Cineca, and I was the PI in an ISCRA B project, Cineca project, for this the investigation on this sponge, and we ran simulations in the order of 700,000 megaloops with more than 7 terabytes of RAM required. And Dr. George Amati, our chairman today, will discuss on the cost of running these simulations, which was really not trivial. And tomorrow morning at 9:40 here in Sala Leone, he will he will take a plenary on this subject, which was an adventure by itself. So this is the results. It's pretty impressive. You can see the geometry of the entire geometry. These white lines represent the division in subdomains for the HPC facility. We have left them. You can see the streamlines. They are all colored with the velocity magnitude. Reynolds 2000, as I told you before, we are in the order of 10 centimeters per second. And this is the flow field at Reynolds 2000. You can see I just give you this flavor now. We will discuss it later, but it's really interesting, and we are still discussing and elaborating the results. You can see that in the region which is close to the sponge, the field is, of course, perturbed by its presence, but downstream, many diameters downstream, the flow field is much more complicated, and we will see how it is possible. This is a remarkable properties of this sponge. So in order to better highlight what happens with such a complex structure, we have realized 4 partial geometries, as you can see here. They are all periodic geometries, so they go from top to bottom of the computational domain. Consider, of course, the basic cylinder, just to validate our results and their basis. Then we have this network structure, the cylinder with ridges outside, and then this structure which is pretty similar to the actual sponge, which is this network with these ridges. Okay, there are no the top portion and the bottom portion because it is considered as periodic, as I told you before, but it is the most the closest to the actual sponge. So we evaluated the velocity components downstream the object. We posed a probe downstream, a little bit decenter far from the little bit with a radius distance from the symmetry axis along the flow direction, and you can see that with the pristine cylinder, pure cylinder, periodic cylinder, you have that at Reynolds 100, the colors stand for the different Reynolds number. You have an attractor-like, an ordered structure for the velocity components until Reynolds 100. Then this order breaks at 500, is already broken, and then it is completely irreversible, so turbulence rises, and the velocity components are completely a mess for the different Reynolds number 1000, 1500, and 2000. Okay, we have done the same analysis for the.
Giacomo, you have
yes.
Giacomo, you have 5 minutes left.
Yeah, yes, I'm jumping to the conclusions. So we compare this field for the cylinder to the fields obtained for the other geometries, and you can see amazingly that both the holes in the net and the ridges on the structure provide a sort of ordering an ordering role on the fluid flow downstream the sponge. As you can see, the velocity components are still pretty close to each other even at Reynolds 2000 with this structure which resembles pretty much the sponge. So looking at the only quantitative analysis that is besides this that is reliable is the drag coefficient. And again, you see, we have not reported here for the sake of clarity the cylinder, which is known, the drag coefficient of the cylinder is known by the book, and you can see that increasing the complexity, so the reticular structure, which is just the net one, then we have the cylinder with ridges and reticular to ridges plus ridges. We see that increasing the complexity of the structure decreases the overall second-D, so the drag coefficient of the experienced by the structure. So what does it mean? It means that all these structural features, holes and ridges, are also in charge of making the structure feel lower drag on it, so the animal can remain anchored to the bottom of the ocean with spending less energy. Okay, and back to Reynolds 2000, we can see this effect in this beautiful movies that Giorgio provided. This is the pristine cylinder at Reynolds 2000. You can see that the intermittency rises immediately and goes on the structure. The presence of the holes on the structure pushes away the vortex wake, and the presence of these ridges with of course have also structural behavior keeps this mess of intermittency downstream to the structure, so the exoskeleton do not feel all the intermittency that is felt 5, 6 diameters downstream. Okay, so these were the results that I intended to show you. We are still processing tons of terabytes of data, but we can draw some conclusions because we have done a state-of-the-art HPC simulation of a full-scale glass sponge in its real environmental conditions. So this object, this animal, lives at Reynolds 2000, and we have simulated Reynolds 2000. We have seen for the first time that this object, besides having remarkable structural properties that are clear to the literature have been clear for the last 15 years, this object has remarkable fluid dynamic performances, and each single structural element has a fluid dynamic role as well. So I have finished. I'm here for your conclusion, for your questions, and thanks very much.
Okay, thank you very much to the speaker. And then I think we have time for a few questions. There is any question?
Dr. Dorschner, I think, has a question.
Yes, please,
hey.
Dorschner.
So thank you very much for Thank you very much for this interesting talk. I just have a question. Maybe I missed this, but you're saying it's such a large-scale simulation. But are you running this on a uniform grid? And if so, why?
Yes, this is a very good question. We were discussing about this with all our colleagues, and before starting them, yes, the grid is uniform, and there is a reason why, because maybe you can save computational resources in terms of RAM requirements, but from computational time, the presence of grid refinements would lead not to such a saving, first of all. Second, we started with our code, which was enhanced and translated into the for the architecture, KNL architecture, and we didn't want to increase, since it was a matter of time also, because we had 9 months to perform all the simulations. It was also a matter of time starting to implement the grid refinement on such a complex code for a complex architecture. So we preferred to have just a plain and validated lattice Boltzmann in order to save the startup time and then be more confident on the results.
I mean, you would be able to make your domain much larger, right? I mean, you wouldn't have any uncertainties with regard to the far-field boundary conditions once you have grid refinement. And also in terms of compute time, I guess, once properly implemented, I guess we've seen this for like cylinder flows and also sphere flows. That too. I mean, the computational time savings, they are quite significant. Or maybe still worth it.
Okay. We discussed many times with George Amati and the other guys, and regarding computational time, we were not so sure. So the overall computational time. Okay, but as I told you before, first of all, the bottleneck was the time duration of the project. We had 9 months to start from scratch and to deliver the results.
Impressive. Thank you very much.
Thanks very much. You're very kind.
Okay, there is any other question?
Can I ask a question?
Sure.
Please.
Yeah, it's a really nice talk. So you have shown data for, in a sense, the coefficient in one particular direction, the drag coefficient in one particular direction. So I'm just wondering if the creature has any interesting anisotropic behavior in terms of drag coefficient if you, let's say, have flow which is at an angle corresponding to the structure. Does it give you anything interesting in that case?
Well, okay, this is a very good question, and we tried to do our best to try to answer this, but of course we did not have the resources, the computational resources, to perform the simulations with any direction of the flow. So we chose if you look at the geometry that I presented you, this geometry is the geometry of the actual sponge is built by the organism in the way that this curvature is downstream. Okay, usually, so it feels the main direction of the stream, and it builds its exoskeleton in this direction, counterflow. Okay, so this is if then there are some others. Other direction, of course, it is possible. Of course, there will be. Maybe there will be also interaction with other sponges around. We plan to, but we need several more computational resources with a praise grant, and so we consider just a preferential direction, which is the one given by this curvature. Okay.
Okay. Thank you.
You're very welcome.
Okay. If there is no other question, I think that we can close the session, and people who want can attend to the other talk that is there's also another talk, yes, on what is Palma room. Okay, thanks again to all the speakers and also to all the attendees.